Hello everyone. Note down this question. It's a water tank and total height of water column inside is capital H. Question is, at what depth from the top free surface a tiny hole should be made so that when water comes out, range is maximum. Go down the question. At what depth x from the top free surface at what depth x from the top free surface a tiny hole should be made so that range is maximum, and also find out this maximum range, should not take more than a minute to solve this question. Good. There are two answers and they both have responded correctly. Look at the approach. First of all, when water comes out, find out u in terms of x. As water comes out, you know that u is root over 2g x free falling distance x up to the position of the hole. And formula for range is what? U times root over h. Which h? This h, which in this case is h minus x. Divided by g. This is the formula for range. U multiplied by 2 this height divided by g. So your range is coming root 2 gx multiplied by 2 into h minus x divided by g. And we need to maximize this range. This r is a function of x and we need to maximize it. If you want to maximize it, technique of maxima minima, it tells us that dr upon dx should be 0. for r to be max, dr upon dx, it must be what? 0. This is from maximum minimum. Now, what we can do is, let's introduce a term y. What is y? R square. What is r square? R square is coming 4 hx minus x square. This is y. So when r is maximum, its square will also be maximum, which means y will be maximum. That means we can say that find out dy by dx, and then this dy by dx should also be what? 0. If r is maximum, r is a function of x, dr by dx should be 0. If r is maximum, so is y, because y is what? Square of r. That means dy by dx, it should also be 0. This way we can save time. Instead of differentiating these square roots, we can now simply differentiate this, which is a much easier task. Let's differentiate this part. What is differentiation of hx? H is a constant. Differentiation of x with respect to x is what? 1. So you got h into 1. Differentiation of x square is what? 2x. And when is this thing 0? When the bracket is 0. And when is bracket 0? When h minus 2x is 0. This gives us x as what? H by 2. So at what depth a hole should be made? At a depth of h by 2. Total height, half of that make a hole. And then when you put this x into this r, what is this x? Maxima, minima. This technique tells you that for this x, which is h by 2, dy upon dx is 0, which means dr upon dx is also 0, which means r is maximum. R as a function of x is given by this. When you put in this, your r max will be coming h. G and G cancel, x is h by 2, h minus h by 2 is h by 2, 2 gone, h by 2, 2 gone, root h is what? H. Now, this and this, these are two standard important results for this type of profile. Whenever they ask you at what depth a hole should be made, half of the height of water column. And what is the range? Range is equal to what? Total height of water column. And you can yourself conduct an experiment like this. Take a bottle, spare bottle, fill the bottle up to the brim, make a tiny hole at exactly at the center, and then when water comes out, you can see that the distance which it travels, horizontal distance, it will be equal to what? Capital H. More or less capital H, because of friction and all, things may not be entirely correct, exactly same, but you will find that it is roughly equal to the height of water in the bottle. This and this, note down these as important results. And remember the technique, whenever they ask you maxima, differentiate and use differentiation in this way. Note down this. Write down surface tension. Suppose you have a liquid in a beaker, then if you look at these three molecules, this one which is deep inside, this one at the surface, this one at the corner. Now, all these molecules, they are being pulled from all the sides by other molecules. Suppose this is a given molecule deep inside. All the neighboring molecules, they are attracting it. Intermolecular forces. These forces are present in all the directions, and therefore a given molecule which is deep inside will experience no net force. F will be 0. इसके चारों तरफ से जो फोर्स आ रहा है, that force is same. Not in 2D, in 3D as well. Just consider a sphere. Why a sphere? These intermolecular forces, they are effective up to a particular range. Just for understanding, suppose this is one molecule and we say that all the molecules up to this radius, they can exert some amount of force on this. Any molecule which falls outside right here, its force is almost negligible. So in a spherical region around this molecule, these are the directions of all the intermolecular forces, giving us a net force of what? 0. Now when you look at the top surface, you will find something like this. A molecule at the top, it is under these forces. Half of the sphere, nothing is present on the top, assuming complete vacuum. If air is present, air will also exert force, but for the time being, forget about that. So all the forces are coming on this molecule are in this form, which tells us that resultant will be downwards, shown with this blue arrow, if you can see it. All these forces, this and this, the horizontal components, they will cancel each other and you are left with vertical components. Any force, their horizontal components will cancel and you can simply add the vertical components, giving us what? A net downward force in this form. And if you look at any molecule which is at the corner, you can see a quarter of a sphere being formed and forces will be like this. Half of sphere, 1/4 of a sphere, and resultant of these will be in this direction. No net force. This is downward force. This is the force on this side molecule. Now, जब अपन इस टॉप सरफेस की बात करते हैं, all these molecules, they are being pulled downwards and therefore they all have a tendency to bring this top layer down. Each and every molecule is under a downward force, as if something is pushing the top surface down. But these liquids are what? Incompressible liquids. You cannot bring this top surface down, because if it comes down, then you're basically compressing the liquid, which is not allowed. इस वजह से क्या होता है, एक ट्रैफिक जैम टाइप का लग जाता है यहां पर. हर चीज कहां आना चाह रही है, नीचे की तरफ, but they're not allowed, क्योंकि जो नीचे के मॉलिक्यूल्स हैं, they cannot move. Because of that, a surface, this is called surface basically, that formation of surface. How do you see a surface? This is that formation of surface. This surface which falls because of this action, because all those things they cannot further come down, this surface formation then creates what? A tension force. This tension force is something we are interested in this chapter of, or this article of, surface tension. Draw this figure. Show these arrows with different color, and then show a downward force with a different color. A molecule which is deep inside, show it in this form. Draw a hypothetical sphere, an imaginary sphere around it, and then show that there is no net force, and do exactly like this for this side molecule, and then we'll write a few statements. Note down these statements. A molecule which is deep inside the volume, a molecule which is deep inside the volume has no net force acting on it, has no net force acting on it. Whereas a molecule which is present, at the top is being pulled downwards, but since liquid is incompressible, this molecule cannot move downwards, thus forming a top surface. Now, for this surface, how do we define surface tension? Look at this. What was observed, if you look at the cross-sectional area of this beaker, this is the cross-sectional area. Side view, and this is your top view. Side view, top view. In this top view, the surface, you're looking at the surface. In this surface, what is observed is something like this. If you draw a hypothetical line, an imaginary line, then it is being pulled from both sides. You know what these forces are? These are these forces, these components. These forces, let's say from one side this is F, from this side is also F, and you know that this F is going to cancel this F. But what is found, that this F and length of the line L, if you go for F divided by L, then it is found that F upon L is always a constant. Force on this hypothetical line coming from one side parallel to the surface is a constant. And in physics we have a tendency, if we find that something is constant, then we try to give it a name. The name which we have given to this F upon L is S, which is called surface tension. So look how each and everything is developing in this setup. The top molecule, it's being pulled down. This downward force is resultant of all the forces which are acting on this. Because of this force, it tries to come down, but it cannot because of incompressibility, thus producing a surface. On this surface, all the forces which are acting in this direction, if you take them as F on a given length L, then force per unit length is called surface tension. Draw this figure, note down this, and then we'll write a statement. Write down the statement. If an imaginary line is drawn, on the free surface of a liquid, then it is found that force acting on the line parallel to the surface on one side, total force is 0, on one side, per unit length is always a constant for a given liquid. For different liquids, this constant will be different. Is a constant for a given liquid. This constant is called surface tension. This constant is called surface tension. Remember, normally tension, when we say tension force, its unit is what? Newton. But this is surface tension, which is force per unit length, and therefore its unit is what? Newton per meter. So write down this. Unit of surface tension is Newton per meter. Unit of surface tension is Newton per meter. In case of a gas, what happens? This molecule is so free that you cannot even form a surface. These forces, they're not that effective. Kinetic energy of the molecule is so large that intermolecular forces, they cannot keep it in a given boundary, and therefore it's free to move. And that's the reason you don't see any surface being formed. It will take the shape of the container in which it is present. Liquids also do that, but the top formation, the top surface, it forms because of this part. Now, how do we handle surface tension now? Let's see this. Well, by the way, what do you think? Mention in the comment box. If we increase the temperature, what do you see? That surface tension, is it going to increase or decrease? If temperature is increased, then what happens to surface tension? What do you think? Good. It should decrease, because if you increase the temperature, these molecules, separation first of all will increase, and as separation increases, that force part will also decrease, and therefore surface tension, force per unit length, this is also going to decrease. Mention this. As temperature is increased, surface tension decreases. Now look at this setup. Suppose we have a U-shaped wire, and on this U-shaped wire we have placed a rod. Length of this rod is L. There is a massless rope connected to this. A massless rope connected to this. Passing through a pulley. Look at the setup. U-shaped wire frame in the horizontal plane, not in the vertical plane, in the horizontal plane. There is a sliding wire. It can slide along the length of the rails. and then there is a rope connected to this running over this pulley, and at the end you have a mass M hanging. What you did, you submerge this whole thing, let's say in a soap solution. जब आप इसको एक सोप सॉल्यूशन में डिप करके बाहर निकालोगे तो आपको पता है कि यहां पर एक क्या बन जाएगी, एक सोप लेयर. A liquid layer is present in this region, remember. A liquid layer is present in this region. We found that for a given mass, this rod is in equilibrium. If this rod is in equilibrium, we can determine surface tension of this liquid. Again, this is a liquid layer, rod connected at this place, rho and M. This M is trying to move downwards, but no, it cannot. It is in equilibrium. Why? Because all this liquid surface is pulling the rod in this direction. And this way we can determine surface tension of this liquid because we have the values for M. Now I'll give you 30 seconds. Let's see who all can answer surface tension of this liquid in this figure. I'll give you a hint because most of you are producing an answer which is close to the correct one. Now I'll ask you a simple thing. This soap layer, how many surfaces are present in a soap layer? Remember, the name of the article is what? Surface tension. So how many surfaces are present? If you hold a piece of paper in your hand, how many surfaces are present? 2. How many surfaces are present? 2. 2. And therefore, most of you thought that force acting is F. Definitely it is F. But another F is present from the bottom surface. So let's write down this as what? F. There are 2 surfaces. So as you attach this rod is being pulled by 2 surfaces, one at the top and the other one at the bottom. And force per unit length for one surface is called surface tension. So this is F, this is F. Let's say from the bottom part, things are in equilibrium. Tension force T, tension force T. This is that tension which you study in laws of motion. Things are in equilibrium. Downward force is what? mg. T is mg. T is F plus F. That is 2F. Which means what is F? mg by 2. And what is surface tension? Surface tension is F divided by L, which gives us mg divided by 2L. तो केवल क्या सोचना था, there are two surfaces, two forces. एक छोटा सा एग्जाम्पल से आपको याद रहेगा. If you take a solid sphere, in a solid sphere, how many surfaces are present? One, the outer one. If you take a hollow sphere, how many surfaces are present in a hollow sphere? Two, outer as well as inner. So this is a soap layer. It has two surfaces and therefore two forces, and therefore surface tension is coming mg divided by 2L. If you understand this, then write down yes in the comment box. Now, draw a separate figure, but first look here. This time we have an external force, and what this external force does, it is going to stretch this layer. With the help of that external, you are pulling this rod. Just imagine a rubber sheet which can stretch easily, and then you are trying to pull the free end. This is a rigid end. You're trying to pull the free end, and that rubber sheet has got what? This internal surface tension part. So, with the help of external force, you're pulling it, and then when you pull it, you stress this thing from this position to this position. We have moved the rod with the help of this external force from this position to this position, and in the process we have produced this much extra surface. Shown with these dots. These lines, they show the original surface area, and the dots, they show the increment in the area. The question is that we are moving the rod such that change in kinetic energy is zero. Change in kinetic energy is zero. Then find out work done by the external force. And leave a line free. We'll be writing the heading in that line. But I want you to answer this part without my help, and therefore I'm not giving you the name of that thing right away. The thing is, an external force is acting in this direction, which is pulling the rod, stretching the whole thing by x, such that there is no change in kinetic energy. The question is that how much work is done by the external force. Write down this work in the comment box in terms of surface tension S. No response. Look at this rod. This is a rod An external force is acting in this direction and rod is being pulled in this direction with these two F. And you know that this F is what? S into L. Now, when I say that kinetic energy, change in kinetic energy is zero, change in kinetic energy zero means acceleration is zero. If acceleration is zero, that means F total on the rod, F total on the rod should be zero. We have zero acceleration. And why do we have zero acceleration? Because there is no change in kinetic energy. Why is there no change in kinetic energy? We'll see that. Now, acceleration is zero, F total on the rod is therefore zero, which means what? F external should be equal to 2F, which is 2SL. SL plus SL. थोड़ी देर पहले यही किया था अपन ने. 2SL was mg and that gave us S as mg upon 2L. Now, that's your F external. Now look here. What is work? Force into displacement. Work is force dot displacement. I'm using D because S is being used for surface tension and therefore I've taken what? D for displacement. How much is the force? How much is the external force? 2SL. What is the displacement? X. What is the angle between these two? 0. Force and displacement. What is the angle? 0. This is giving us S 2LX. Now who will tell me what is 2LX? Well, only one person has answered S into 2L into X, but now tell me what is this term? The entire term 2LX, what does it represent? Let's say, what is this length? L. L into X will give you what? Area. But if you stretch this thing, how much is the change in surface area? Can you see that? कि आप दोनों तरफ surface को increase कर रहे हो, Lx on this side and Lx on the bottom side, which means what? This 2Lx is for us S multiplied by delta A. What is delta A? Change in the surface area. Remember, on one side change in area is what? L multiplied by X. ऐसा ही पीछे की तरफ हो रहा है. तो टोटल कितना आपने एरिया डेवलप किया? 2Lx, which will be called what? Delta A, and this is your W external. Now tell me this. What is this W external basically? And the hint is we have left one line for the heading. So what do you think this S delta A is? Good. This is surface potential energy. Work done by external force. Work done by external force. It changes kinetic energy. It changes what? Potential energy. Delta K as being kept 0, we have found delta U potential energy, delta change, and W external is coming what? S multiplied by delta A. So this is giving us delta U as S multiplied by delta A, or U is S multiplied by A. This U is called, which is the heading of the article, surface potential energy. If you understand up to this point, U equals to SA, everything completely, then write down yours in the comment box. And if you are confused, just tell me what your confusion is. And in that line which you left, write down the heading now, surface potential energy. Now write down the statement. Work done by an external force, work done by an external force in increasing surface area of a liquid layer gets stored in the form of surface potential energy. Provided there is no change in the kinetic energy. Provided there is no change in the kinetic energy. Now, we can also write this statement in this form. What is S? Delta U upon delta A. Or you can write du upon dA in this form also. Let's use delta for the time being. What is surface tension? Surface tension was force per unit length. And now surface tension is what? Change in surface potential energy per unit change in surface area. You can also define surface tension in this form. The statement which you just wrote, it tells you what the entire work done by the external force gets stored in the system in the form of what? Potential energy. Provided you're not changing kinetic energy part. So I gave you 100 rupees. You've got two pockets. One is called kinetic energy. The other one is potential energy. You're not allowed to keep any money in your kinetic energy pocket. So whatever money I give to you, that increases your potential energy count. That's what we are doing in this part. And then what we are saying is change in surface potential energy per unit surface area, change in surface area is a constant. And this constant is called what? Surface tension. Write down this and then write down the statement. Change in surface potential energy, change in surface potential energy per unit change in surface area, per unit change in surface area is a constant for a given liquid, is a constant for a given liquid and is called its surface tension, and is called its surface tension. So the earlier S was what? F upon L. So this gave us unit as what? Newton per meter, F upon L. Now S is what? Delta U upon delta U. What is delta U? Joules. Delta A meter square. So write down the second unit of surface tension. Another unit of surface tension is joules per meter square. Joules per meter square. Now this gives us a mathematical way of explaining things. Now, everything in nature has a tendency to be in a state of minimum potential energy. If you drop this marker, it is coming down. You can say because there is a force of mg, or in terms of energy you can say that it is coming down because its potential energy is decreasing, and everything tries to be in a state of minimum least potential energy. हमने एक स्प्रिंग को खींचा, छोड़ते हैं तो कहाँ जाती है? नेचुरल लेंथ पर, जिससे कि उसकी पोटेंशियल एनर्जी क्या हो जाए? जीरो हो जाए. Now there is a statement, and remember the statement. Write down the statement. For a given volume, well, let me ask this first. Maybe some of you already know this thing. What I'm asking you is, you have a given volume of water or any liquid, or for that matter, anything. For a given volume, how many different types of shapes you can produce? There is no finite number for that. You can create any number of surfaces. Let's talk about some standard surfaces. So you have a cylindrical volume. You have water, put it inside a bottle. It takes what shape? Cylindrical. Put it inside a cube. It becomes a cube. Put it inside a spherical ball. It becomes a sphere. So it can take so many surfaces, and all the time you've got same amount of volume. You've got 1 liter of water and you have put it in different shapes. The question is that for which surface area will be minimum? If you have the idea, if you have this knowledge, it is also kind of general knowledge type thing. For a given volume, what is the shape which has minimum surface area? If you know it, then answer this thing in the comment box. No response? Don't worry. Now complete the sentence. For a given volume, surface area of a sphere is minimum. For a given volume, surface area of a sphere is minimum. And you can verify this thing for standard shapes. Do what? Take mathematically, just take 1 meter cube of water. What is 1 meter cube of water? A cube of 1 by 1 by 1. 1, 1, 1. Now, so what is the surface area? You know 6. How many faces do you have? 1, 2, 3, 4, 5, 6. What is the area? 1, 1. That will give you 6. If you have 1 meter cube of water and you put it inside a cube, how much is the surface area? 6. Now, entire volume of this 1 meter cube, put it inside a spherical shape whose radius is what? R. 4 by 3 pi r cube is 1. This will give you R. What is the surface area? 4 pi r square. Compare this 4 pi r square with 6 and you will find that 4 pi r square is less than 6. So for 2, I've told you how you can verify this thing. But now remember the statement, any shape which you form, if you measure the surface area, the minimum you will find when entire volume is in the form of a sphere. Now look here. What is potential energy? Surface tension into area. और अपना आर्ग्यूमेंट क्या है कि दुनिया की हर चीज किस तरह से रहना चाहती है जहां पर उसकी एनर्जी क्या हो, मिनिमम. तो अगर एक गिवन वॉल्यूम हमने बनाया और अगर उस गिवन वॉल्यूम को हमने एक वाटर ड्रॉप तो ये जो ड्रॉप थी ये क्यूबिकल क्यों नहीं थी? Was it not cylindrical? The reason is, for a given volume, if it takes a spherical shape, then surface area will be minimum and therefore potential energy will also be minimum. And everything wants to be in a minimum potential energy state. Now, on the next line, write down the statement. Shape of a water drop is spherical. Shape of a water drop is spherical because surface area of sphere is minimum and therefore its surface potential energy is minimum and everything has a tendency to be in minimum potential energy state. Everything has a tendency to be in minimum potential energy state. और ये तो energy wise हो गया. Otherwise, just try to imagine this very first line which we started, surface tension. Imagine a volume. It has any orbit shape, but all those things which are forming the surface, all those molecules, they are being pulled inside. Now every molecule which is being pulled inside, all the molecules, they have identical conditions. They should be in an identical shape. So if you give them a corner, type of thing, if you try to keep everything in the form of a cube or in the form of a sphere, this molecule and this molecule, they are under different conditions. If you keep them in the shape of a cube, these are being pulled inwards, and all these are being pulled inwards. Now, in this case and in this, for this molecule and for this molecule, things are different. They are under different forces. This and this, these two positions being different. And therefore, there is always a chance that this one wants to move to this position or this one wants to move to this position, because they find that conditions are different at both places. That means there is no permanent equilibrium if a liquid is left in a free state in this form. Whereas if you look at this form, every point on the surface is experiencing same type of force. तो किसी भी मॉलिक्यूल को ऐसा नहीं लग रहा कि मैं यहां से यहां चला जाऊं तो मेरी हालत अच्छी हो जाएगी, जैसा यहां था वैसा ही यहां है, वैसा ही यहां पर है. And therefore they are always in a state of equilibrium. This is the force concept. And you define the same force concept in terms of potential energy using this part. Now, write down a question and let's see how many of you will answer it. First, let's write down the question. A big drop of water splits into n identical smaller drops. A big drop of water splits into n identical drops. First tell me, surface potential energy is going to increase, decrease, or will remain same? What do you think? First answer should be in terms of increase, decrease, or same. You have a big drop, you split the whole thing into n identical drops. In the process, what I'm asking you is, surface energy, is it increasing or decreasing, or does it remain same? And then try to find it using maths. First, your opinion, what do you think, what your gut feeling is, and then go for the mathematical version of that. And this will give us some interesting fact. The question is that what happens to surface potential energy when a big drop like this splits itself into smaller drops? Look here. हालांकि इंट्यूशन में कुछ चीज होती है and it tells us that surface area should increase. Well, let's start with this. Radius of this drop is capital R, and all these drops, their radius are small r. एक एक करके आंसर देते जाना कमेंट बॉक्स में फास्ट। फर्स्ट केस में सरफेस टेंशन ज्यादा होगा या सेकंड केस में? राइट डाउन दिस। फॉर लार्जर ड्रॉप or for smaller drop, for which one surface tension will be more? Write down this first. For which one surface tension will be more? Well, only the first answer is correct. It will remain same. Surface tension, it depends on what type of liquid and the temperature. It doesn't have anything to do with surface profile. It can be any surface. So remember, surface tension will remain same. This is also a good question for you, in fact. So you can write this as a question also. Which one has greater surface tension? Answer is S. Answer is S. Surface tension will remain same. Now, what is initial area? Initial surface area. 4 pi r square. What is final surface area? 4 pi r square, and there are n such drops. Surface area 4 pi r square, there are n drops, n times. Initially the whole thing is this. But answer this fast again. In which case you have more volume? When it is in the form of a big drop, or when it is in the form of these smaller drops? I'm asking for total volume of this and total volume of this. Which one is greater? Answer this. Initial volume is what? 4 by 3 pi r cube. And final volume is what? 4 by 3 pi r cube, and there are n such drops. And good, at least you have answered this part correctly. Volume will remain what? Same. यहाँ से यहाँ आ जाओ, volume पर क्या असर पड़ेगा? कुछ नहीं. So initial volume and final volume will be same. 3 pi cancel. We got small r as r divided by n to the power 1 by 3. 4 by 3 pi gone. Small r, take cube root, divide by n, cube root 1 by 3. Put this value of r over here. It becomes n into 4 pi small r, which is this r square upon n to the power 2 by 3. Square of this. This is n to the power 2 by 3, and if everything is correct, then this is coming n to the power 1 by 3 4 pi r square, or n to the power 1 by 3 a initial. So final area of all these drops taken together is cube root of n times initial area. Let's say we had a single drop and then it splits into 8 identical drops. 8. So you split the whole thing in 8 identical drops. Cube root of 8 is what? 2. इसका मतलब सरफेस एरिया क्या हो जाता है? डबल. ध्यान रखना, जब भी आप इसको ब्रेक करोगे, जो आपका सरफेस एरिया है वो हमेशा क्या होने वाला है? Increase होने वाला है. And therefore again, when a big drop splits, its surface area increases, which increases what? Surface potential energy. Let's write down the change in surface potential energy. Delta U. Surface tension multiplied by delta A, which is coming S into A final minus A initial, which is coming as S into 4 pi r square common. This is a final n to the power 1 by 3 minus 1. ये सिंपल है, कुछ खास नहीं है. अपने को क्या फाइंड करना है? डेल्टा यू एस इंटू डेल्टा ए. पूरा दिमाग ए फाइनल फाइंड करने में था. तो दिस इज योर डेल्टा यू एस टाइम्स 4 pi r square cube root of n minus 1. For n equals to 8, 8 cube root 2 minus 1, 1. Change in surface energy will be s into 4 pi r square. Interesting part is what? Surface energy, surface potential energy is increasing. Now, the interesting part which I told you earlier, that there is a very interesting fact involved with this. Now understand that when you take shower, you must have felt that drops, the temperature of a drop as compared to the normal temperature right at that time, you will find that it has slightly less temperature, and therefore we always use fountains and all because they lower the temperature, they save us from excessive heat and all. Now what is happening during when a fountain works or when you take shower and all, you're converting a small surface area into a larger surface area. When a fountain works, when you take shower, you're converting small surface area, A initial, into a larger surface area. And in this process, you are increasing what? Surface potential energy. There must be some external force which increases this potential energy, but there is no external force present. Then you have to conserve total energy. If somebody is increasing the potential energy, then it must be compensated somehow. How come this energy is increasing? There must be something which decreases at the same time, and that is thermal energy. So thermal energy of water molecules, it decreases. That means its temperature decreases, and therefore you always observe that when you take shower or when you're near a fountain, temperature is a bit lower. Write down this last line. When a water drop splits, surface area increases, which increases surface potential energy. But as no external work is present, COME tells us that, conservation of mechanical energy tells us that some other form of energy should decrease. Some other form of energy should decrease. This energy is thermal energy of water molecules, and this is the reason near a fountain temperature drops. If you understand everything in today's lecture, then write down yes in the comment box and then you can leave. Thank you very much.